the next session on holistic approach to clean coal, energy and mining management by Dr. Shen Sen, who is a professor, Department of Civil Engineering and Environmental Engineering at the University of North Carolina at Charlotte, and the State Key Laboratory of Geometrics and Deep Underground Engineering at the China University of Mining and Technology at Zhizhou, China. Dr. Chen's research interests are in the areas of shock and vibration, geophysical testing, structural health monitoring, non-destructive evaluation, coal mine effects mitigation, and carbon sequestration. He specialized in laser-based vibration sensing techniques. Dr. Chen is the co-principal investigator of a Southern Company initiative in carbon sequestration in Alabama since 2002. The project has since injected more than 7,500 tons of CO2 in the Rodessa formations in Alabama. He's currently working with the China University of Mining in carbon sequestration in coal mines using mineral sequestration techniques. I request Dr. Chen to kindly deliver the session.
So my presentation is on the downstream of CCS. So our research is regarding how do you geologically sequester CO2. And my presentation is going to be a little bit skewed. I will be intermeeting different ideas of this carbon capture, not capture, but storage experience. Okay, so a brief research timeline of our research on carbon sequestration at Charlotte. We started in 2002 working with Southern Company on determining whether the Citronelle oil field is a good candidate for carbon sequestration. Citronelle oil field is an old field. It was discovered in 1955, and the oil producing layer is at about 11,000 feet. I apologize, everything is in US units. And the oil has gone through primary and secondary production stage. So it has been water flooded, and back in the 80s, most of the wells has been shut down because of the low oil production. And we found out that in 1981 to 84, there was actually a prior CO2 EOR project that was being proposed. But because of the dispute between the oil producer and the Department of Energy, that project has never been carried out or concluded. So ours is actually the second phase of actual CO2 EOR at this field. Going back, we have since 2010 working with the China University of Mining Technology in developing a technique of sequestering CO2 in existing coal mines as part of their generation and backfilling technology. And I will explain a little bit on different enabling technology that we're developing. So this is the ongoing research that we are doing. And the Citronelle project is on its winding. So January 30th will be ending this phase of the project. A little bit about the Citronelle geological formation. This picture shows two stages. Because the oil layer, the producing layer, is only 400 feet in thickness, so you can't see it from the grand scheme of this picture. So at about 11 to 12,000 feet, you can't really pinpoint the exact formation, but it's embedded in a dome-shaped geology formation, and this is a really neat area because it has a four-way closure. So the fault lines kind of traps the oil-producing dome in this area, and this whole region has about 500 plus oil-producing wells. So the infrastructure has already existed way back then. All we have to do is just open up the wells and then start injection. And this shows you the location. So this is on the southern tip of Alabama, and this is Florida. And the Citronelle is about 40 minutes drive from Mobile, Alabama. So it's relatively inland, and it has most of the geological formation is due to the tidal formation. So delta strata. And as a result, you can see that the formation is not uniform layers. Okay, in fact, it consists of several pockets of oil, and so the oil producing previous producers kind of hit and miss in their product. And this shows you the matching up of geophysical data that we have kind of composed together. We spent 2 years to compose all the 500 different well data together. We use the method passive geophysical testing to monitor the injection process, to just show you the analytical procedure to create the soil stress or the geomaterial stress profile. And we use this technique to monitor the production stage, the injection stage. And these are the two lines of study. So with 2 lines, you were able to produce two-dimensional profiles. And the goal of this 2 lines is because we wanted to get a sense of the direction of where the CO2 may be going. The 2 lines centers on the injection well, so all the CO2 were injected in one well, which is 119 at this location here. And both of the lines are about little over 25,000 feet in entire length. Okay, this is the history of our injection process. So, way back in 2008, we started to inject water because the well has not been active for so many years. The pressure in the layers has already been reduced. So you have to use water to build up the pressure to 4,000 psi. And then in 2009 December, we started to inject CO2. In the beginning, we were not successful in pumping the CO2. We had a lot of problems. The pump wasn't working, but nonetheless, by September, 2010, we started to be successful in injection. And at the end of 2010, we have pretty much completed the 7,500 ton CO2 injection. And then we are currently using water to maintain the pressure and also monitor the migration of the CO2. In fact, at the beginning of this year, we realized that there is a sudden drop in the oil production. So this is one of the things that in geological sequestration that you encounter, there are a lot of uncertainties. And so without knowing exactly where the CO2 is dispersing, it's very difficult to quantify or find out the cause why we have an oil production drop. This shows you the amount of CO2 injected history. So by January of 2010, we started successfully injecting the CO2 continuously, and we used the huff and puff method. And this shows you the oil-producing layer stress correlation to the well pressure, so it's quite consistent, and we're quite happy with this result. The next result is really the critical component. So from our geophysical testing, we realized that after the water injection at 4,000 psi, the pressure on the strata has built up. However, when we start to inject the CO2 into the formation, we realized that there is a consistent increase in the pressure of the strata above. So this is like a membrane effect. Okay, when you have a very small layer of CO2 being injected, even though we have about 11,000 feet thick of the layers above, but in the grand scheme, it's like a balloon. So you have that membrane issue. So this tells us two issues. One is that our capping material will be in hydride layer. So I'm going to mention that right above the sand rock that's all bearing, it actually has a layer of anhydride that kind of traps the CO2. And this shows us that that layer of anhydride is working. So we have certain, but nonetheless, it still brings concerns to our group because we realize that the stress has increased by 10%. So if we continue to inject CO2 and there's no oil production, then by monitoring the stress growth, we may be able to predict a breaking point of the fracture of the anhydride layer. So that is the geological sequestration in the oil field for EOR purpose. Now, we also did some study on all the quantified potentials of geological sequestration. So since 1980 to 2010, the total global CO2 emission comes out to be 721.1 gigatons. Okay, and if we quantify all the coal seams, all reservoir and saline formations that you can sequester CO2, it comes out to be 690 gigaton potentials. Okay, so we don't really know if that amount is really exists. However, you see the differential between the two numbers. So there is still a significant amount of CO2 that has been produced since 1980 that will not be able to be contained in any of the currently proposed geological formation. And so we approached another method, which is called the materials sequestration. So going back to the holistic approach of coal mining backfilling method, we work with the School of Mining because they have a patent technique that they can dig coal and at the same time use backfill to stabilize the mines. Okay, and in this technique is not popular in North America because we use the room and pillar method. Okay, and usually we just leave the mines abandoned after completion of production. But with the School of Mining, they're interested if we can pump CO2 and then just blend that material into the backfill material so that you can sequester both the waste, solid waste, and also the gas that was being produced from coal-fired production. And we found that this integration of two technology has a lot of benefits. One of which is it really brings another business model for the coal miners. Okay, so the mining companies are interested in this because now that the mines are no longer just a production element, but it can also be used as if it's a waste reduction material. And also it's good for the environment and many other benefits. One of which is that because you utilize the land void, you can reduce land subsidence, which is very common among abandoned coal mines. Okay, so the holistic management integral of mining operation require that the mining companies, it gives an opportunity for the mining companies to work with the existing infrastructure such as the energy companies as well as the municipal office. And the goal is to use the coal mines, the mine voids, as a waste storage or energy storage. Okay, so if you have a lot of off-peak wind or solar energy productions, you can use that energy to produce CO2, and then you can store CO2 as H2, hydrogen, as a form of energy. And this is a technique ideal for mines close to city area. So working with Shuzhou, China, they have coal mines pretty much surrounding the city. So now they are also interested in possibly using those coal mines as a land management resource. Okay, the core technology in HMI is the waste backfill material with CO2 storage capacity, which is what I'm going to present next. Okay, so this is schematic of what we envision the holistic management interval between the different elements. And of course, the elements would consist of the mining operations, energy operations, municipal operations, and different entities of interest, such as concerned citizens or environmental justice societies. This is the core technology of our proposed technique, which is a method of blending ash, cement, and CO2 into a porous material. So it's very much like the AAC, which is the aerated concrete. We call it ACC because now it's aerated carbonated concrete. And the essential idea is use the calciums in cement to bond the carbons in the process of carbonation. But by producing porous materials, we also encourage physical sequestration. So the pore space can actually physically trap the CO2 in the pore area, and then over time, that CO2 can be absorbed again into the matrix through carbonation, and then recreate void space, so that you can now have secondary injection. So this becomes a business model because you can multiple injection into this material. But the challenge of this study is that it's multi-physical. So you have to understand how gas flow into this dual porosity material, and at the same time understand how the chemical reactions can be optimized. As well as since now that you have produced a material, which essentially if you use pressurized gas injection, the material may expand. So when you backfill this into the coal mines, you have to be concerned about the possibility of stressing the strata of the mine void. And so we are simultaneously doing two studies. So in the material development aspect, we developed this reaction chamber because you wanted to quantify exactly how much the CO2 is being absorbed. Okay, especially we are concerned about both chemical and physical absorption process. I'm not a chemist, so I kind of need to use absorption, all the absorption words, so please apologize for my misuse of lingos. But this is the way that the reaction chamber works. So we put the reaction chambers, both the reference cell and the reaction cell, in a water bath. And so that we, by monitoring, since we are keeping the temperature as a constant, by monitoring the pressure drop, we will be able to quantify relatively how much CO2 is being absorbed into the process. And because we built the chamber at a relatively large size, we were able to test materials with significant amount of quantity. I mean, significant in the sense that we are looking at maybe 30 grams of blended material. So from a statistical point of view, our representation is more easier to project into a full-scale system. And this is our preliminary results. We have been able to use pressure drop to identify evidence of actual absorption of CO2. So in you can look at this picture as if it's two clusters of curves. So the above clusters are where we are using cement as it is. And the bottom lines are cement with a reaction agent. In this case, we use aluminum to create a void space. Okay, and so using these two sets of curves, you can quickly identify that yes, within so the timeline here represents 48 hours, 2 days. Within 48 hours, we were able to identify that there are some chemical absorption. So these are permanent removal of CO2. It's being fixed by chemical bonding, carbonation. And but once we generate the porous area, you can see that there is a significant amount of CO2 actually is being trapped in the void space. So this gives us a lot of encouragement. And the best result we have come out with at this point is about 20% of CO2 relative value is being trapped into the material that we have created within 48 hours again. These are some SEM and EDS results. The SEM result shows that this is a non-carbon reacted material. So with 90% of ash and 10% of cement, you can see a lot of ash. These are fly ash. So you can see the spherical structures. And if you have reversed the combination, then you see a lot of clay-like structure, which are the cement matrix. And then we add aluminum into the mix, and this shows evidence of dual porosity. So we have large pore space and small pore space, and some of these pore space are interconnected. So when we re-inject CO2, they can go through and backfill those materials. And we are right now doing a lot of studies, numerical simulations to determine what is the effect of colors versus just separated pore space. And this is another encouraging picture. So you see that aluminum forms a crystalline materials within this. I think it's, I don't exactly know what the chemical is, but it has this formation. And this is neat because then we can verify what happens when carbon is being added to the mix. So this is without carbon, and you can see the formation of this with only aluminum. It has a very crystal sharp structure type. But when we add carbon into the mix, then you come up with this fibrous matrix, and all these are carbonates, calcium carbonates. Okay, and so with this, and also with the results of EDS, we confirm that there are actual calcium carbonate formations in our mix design. Okay, so in summary, the benefit of carbon concrete is that it depletes coal waste, not just the solids, but also possibly mine pools. So we are now studying to use pool water, mine pool water, to see if we can use that as the mixing liquid and CO2. And the most important thing, contrast to other geological sequestration techniques, we show evidence of chemically fixation of CO2. So this is a permanent removal of the CO2. And we stabilize coal mines using it as a backfilling material, and also and you avoid mine subsidence. And the porous material has the potential of multiple gas injection in the long run. Okay. Now, because the material may expand, so we have to monitor how it's formed. So we also do monitoring development. So we use fiber optics, and we create this cylinders material because we wanted to be able to determine how rocks may be fractured due to the expansion of material. And this shows that we put the FPG sensors around the cylinder, and then put the expansive materials in the middle of this setup. And so, based on the first mode of fracture, we were able to determine the mechanics of this material. Okay, we did some experiments. These are just some of the results. We are continuously producing with different, because the cylinder formation process is still not perfect. So our have different outer and the inner radius. So vortex is different. Okay, but using fiber optics, well, when we inject the materials in the middle, you can see that the material suddenly starts expanding. Within 24 hours, we were able to recognize the mark-off cracking of the cylinder. And then using fiber optics, you quickly realize that, hey, we can capture the entire history of the fracture process. So this shows you the expansion material straining the cylinder, and then when you start fracturing, you have a drop in the stress, and you can capture multiple drops. These are very encouraging results, and we do I hope this will work. Numerical simulation. Okay. So we did the finite modeling. I don't think it's going to work, so that's fine. But using the strain readings, all of the fiber optics, we can predict the exact location of where the fracture may exist. So our current plan is to put these linings into the coal mines so that we can, as we do this process, we can monitor the coal mine rock formation stressing. And the reason we choose fiber optic is because in China, a lot of the coal mines are saturated with methane or shale gas. So if you use any kind of electronic-based monitoring systems, the possibility of creating coal fire is dangerous. So we choose to use fiber optics method. These are just more of the advanced studies of this. Okay, so in summary, the holistic coal mining management strategy is a next generation of green mining technique. So back in the 2000 to 2010, there is a lot of studies of so-called green coal mining techniques, which basically use a lot of methods techniques to ensure safety of mining practice as well as minimization of environmental effects. But using the holistic mining integrals, we suggest new material science as well as better utilization of the underground cavities or voids, and also the integration with infrastructure management. And I'd like to acknowledge we just recently received a grant from China's Natural Science Foundation, which will start end of this month. So we have 3 years of continuous studying on this topic. Thank you very much.